Hello class, in today's video I'll be talking about 3.7 implicit functions. Remember, while watching the video, write down important vocabulary, formulas, equations, pause if you need a moment to process what was said, rewind and repeat if you did not understand something, and remember to identify what questions you still have. After you watch the video, write a brief summary of what happened in the video and submit this summary via the online whisk. Let us begin. So before we go into deriving implicit functions, let's review, take a look at how we can derive explicit functions, since the skills we learned in deriving explicit functions will be used in deriving implicit functions. So let's take a look at this example, this classic example of a power function, y equals 3x squared plus 4. So as we learned in the power rule, taking the derivative of this function would be, first we take d dx of both sides, d dx y equals d dx of 3x squared plus 4. Now we can divide this 3x squared plus 4 into two parts. So d dx of 3x squared plus d dx of 4. So now, according to the power rule, this part would equal, so d dx of d3x squared of dx would equal 6x. And as we all know, the derivative of a constant would always equal 0, plus 0. So we can conclude that dy dx here is 6x. So now, using these skills, let's take a look at how we can derive implicit functions. Okay, so here is an example of an implicit function, x squared plus y squared plus 4. So this is obviously a circle. So just like we did here in deriving explicit functions, let's first take the d dx of both sides to find the derivative. So d dx of x squared plus y squared equals d dx of 4. Now, like we did when we were deriving 3x squared plus 4, we can divide this part into two. So d dx x squared plus dy squared dx equals, and as I mentioned above, the derivative of a constant is always 0, equals 0. So now this part, according to the power rule, is obviously 2x. Dx squared of dx is obviously 2x. Now the question is, what is this? So this is saying find the rate of change of y squared in terms of x. So let's do this. Since this is a bit new and complicated, let's do it separately. I'm going to change pen color. So here. So let's just assume h is defined as y squared. So let's take the derivative of h in terms of x. So dh dx equals dy squared over dx. Now, this is something we learned in the chain rule, so we can express dh dx like this as a product of dh dy multiplied by dy dx. Now, dh dy, this looks quite familiar. We can find this out by using this. So let's use another color. So let's derive this in terms of y. So dh dy equals y squared dy squared dy, which equals 2y. Now, so we can use this 2y and substitute it here. So now we can get, so this equals 2y times dy dx. So this whole thing can be substituted here. Oops. This whole part here can be substituted here. Oops. So if we rewrite it, it would be 2x plus 2y times dy dx, which equals 0. Now, we subtract 2x from both sides, and then we would get 2y times dy dx equals negative 2x. Thus, we can conclude that dy of dx equals negative x over y. Now we see something strange or unfamiliar here, which is that here the dy dx, the derivative of y in terms of x, is not only is dependent on both y and x. So if we take a look back at the explicit function here, we can see that dy dx is expressed in term is only dependent on x, but here it's dependent on both x and y. As we can see, it is negative x over y. So this might be a little confusing, so let's take a look at the graph of this function, x squared plus y squared equals 4, to see what this means. Okay, so this is the graph of x squared plus y squared equals 4. As you can see, this graph is this is the shape of a circle. So coming back to the derivative of this circle, dy dx equals negative x over y, we can see that this is dependent on both x and y. This is because x squared plus y squared equals 4 is a circle. In other words, it has two corresponding y values for every single x value, which means that it will have two different derivative values at one x value. So for example, let's take x equals 1 as an example. Here, if we calculate the y value through the explicit form of this function, we get the y value is, at x equals 1, is plus or minus 4 minus 1, which means it's plus or minus 3, square root of 3. So one corresponding y value would be here, in this case, positive root 3, and another would be here, where the y value is negative root 3. So at these 2 points, the derivative values, or the slope, would be different. So here at the positive, at the first quadrant, the slope would be positive, and at the fourth quadrant, the slope would be negative. So using this method, we will be able to find the derivative of every single point of this circle except for 2 points, which are here 2, 0, and here negative 2, 0. So you might be wondering, why only these 2 points? So let's take a look at the derivative again. Dy dx equals negative x over y. So one thing to notice is that the y is in the denominator, and one thing we know is that the denominator can never be 0. But here, at these 2 points, 2, 0 and negative 2, 0, the y values are 0. In other words, the denominator becomes 0, which means that the derivative don't exist at this point. Okay, so now that we have seen how to implicitly differentiate a function, let's take a look at some more examples. Okay, so for our first example, we have find dy dx for ln x plus ln y squared equals 3. So like we did on our previous problems, let's first take the ddx on both sides. So ddx of ln x plus ln y squared equals ddx of 3. Now we divide this part into 2. ddx ln x plus d dx ln y squared equals 0. So, and as the derivative of a constant is always 0, so now we know that the derivative of ln x is 1 over x, so we can rewrite this as 1 over x, and we can take the derivative of this similarly like the way we did at when we were deriving the circle equation. So this would equal y squared 1 over y squared multiplied by first using the chain rule 2y, and then rewrite dy dx, which equals 0. Now, we want to rewrite this in a neater form, so as we can cross out the y here, the two y's, so y squared and y can cancel out, and so this would equal 1 over x plus 2 over y dy dx equals 0. So dy dx equals negative 1 over x multiplied by 2y over 2. So negative y over 2x would be our final answer for dy dx. Now let's move on to our next example. So the previous example we just did was fairly easy. It was fairly straightforward. I guess you guys won't have much problem with it. So let's just take a look at a rather challenging example. So let's try deriving y equals x to the power of x. So this function might look like a power function, but it's actually not. It might look like a power function, it might look like an exponential function. So there's a special way of deriving this. So before we take the d dx of both sides, what we want to do is we want to take the ln on both sides. So ln y equals ln x to the power of x, and we can use the properties of ln to find out that ln y equals x times ln x. Now we can use ddx on both sides. So ddx ln y equals ddx x times ln x, which then we can figure out that this side would become 1 over y times dy dx, and this side becomes, so we use the product rule here. So first derive 1 times ln x plus x times 1 over x. So basically ln x plus 1. So we can multiply both sides by y. Let's do it in another color. So multiply both sides by y here too. Then these two will cross out to become this side becomes dy dx. And then here will become y ln x plus ln x. Oops, let's rewrite this. This will become, better. This will become y ln x plus y. So we found dy dx equals y ln x plus y. Okay, so this is what I have for today's video on differentiating implicit functions. I hope you enjoyed it. Thank you.